But it's number theory and methods of proof. So direct proof and counterexample 1. Introduction. Both discovery and proof are integral parts of a problem solving. When you have discovered that a certain statement is true, try to figure out why it is true. If you succeed, you will know that your discovery is genuine. Even if you fail, the process of trying will give you insight into the nature of the problem and may lead you to discover that the statement is false. For complex problems, the interplay between discovery and proof is not reserved to the end of the problem-solving process, but rather it is an important part of each step. So, assumptions that we make in these in this chapter when dealing with number theory. Familiarity with the laws of basic algebra. Let's see here. Equality, 3 properties of equality. Principle of substitution. If A equals B, then you can substitute B wherever we have A. Assume there's no integer between 0 and 1, and that the set of all integers is closed under addition, subtraction, and multiplication. This means that sums, differences, and products of integers are in themselves integers. It's not closed under division, of course. Even odd prime and composite integers. An integer n is even if and only if n equals twice some integer. An integer is odd if and only if n equals twice some integer plus 1. Symbolically, n equals 2k for some integer k if n is even. If n is odd, then n equals 2k plus 1 for some integer k. Use the definition of odd and even and odd to justify your answers to the following questions. Is 0 even? Not a trick question. Yeah, it's even because it's 2 times 0 is 0. Is minus 301 odd? Yeah, because it's 2 times minus 151 plus 1. If a and b are integers, is 6a squared b even? Yeah, because 6 is an even number, so it's 2k, 2 times 3 times a squared times b. If they are integers, that 2 or 3 times a squared b is also an integer. 2 times that integer makes it even. If a and b are integers, is 10a plus 8b plus 1 odd? Yeah, same logic applies there. You can write it out as 2 times some integer plus 1. Is every integer either even or odd? Yeah, there's no oddball sitting out there that's neither one or the other. So yeah, and goes through Logic, yes, every integer is either even or odd. However, the reason for this fact is not immediately apparent. It can be deduced using the method of proof by contradiction. It is also a consequence of the quotient remainder theorem, which we will get to later. An integer n is prime if and only if n is greater than 1, and for all positive integers r and s, if n equals r times s, then either r or s equals n. An integer n is composite if and only if n is greater than 1, and n equals rs for some integers r and s, where r is between n and 1, and s is between 1 and n. Symbolically, for all integers, all positive integers, r and s, if n equals rs, then either r equals 1 or and s equals n, or r equals n and s equals 1. And the composite number is not prime, basically. Is 1 prime? Is 1 a prime number? Nope. A prime number has to be greater than 1. Yeah, it was in the definition before. Is every integer either greater than 1 either prime or composite? Yes. It's one or they're one or the other, if it's greater than 1. What are the first 6 prime numbers? Two, 3, and what was 5? No, not 6. Because 6 is 2 times 3 is 6. Sounds about right. Yeah. 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 Write the first 6 composite numbers. What's the first composite number? 4, 6, 8. Missed one. 9, 10, and 12. Yeah. No, a prime number is required to be greater than 1. Yes. What was that second question? Yeah. Yeah. Yes. Yeah. It goes through the explanation of composite and primary. 2, 3, 5, 7, 11, 13. 4, 6, 8, 9, 10, 12. Proving existential statements. According to the definition, a statement in the form there exists an x in D such that Q of x is true if and only if Q of x is true for at least one element x in D. One way to prove this is to find an x in D that makes Q of x true. Another way is to give a set of directions for finding such an x. Both of these methods are called constructive proofs of existence. The logical principle underlying such a proof is called an existential generalization. It says that if you know that a certain property is true for a particular object, then you may conclude that there exists an object for which the property is true. Prove. There exists an even number n such that it can be written in two ways as a sum of two prime numbers. Yeah? An even integer. Written in two ways as the sum of two prime numbers. This should be a positive even integer, because you wouldn't be able to write it. Prime numbers have to be positive, so sum of two prime numbers would have to be a positive number. Suppose that R and S are integers. Prove there exists an integer k such that 22r plus 18s equals 2k. Yeah? You just solve for k in terms of R and S, so it would be 11r plus 18s, and you can solve for S and R in terms of k and the other integer. Let's see here. A, let n equal 10. 10 equals 5 plus 5 equals 3 plus 7. And 3, 5, and 7 are all prime numbers. Thus, there exists an even integer, namely 10, that can be written in two ways as a sum of two prime numbers. Proof by example. Existential generalization. Let k equals 11r plus 9s, then k is an integer because it is a sum of products of integers. And by substitution in the distributive law of algebra, 2k equals 2 times 11r plus 9s equals 22r plus 18s. Thus an integer, namely k, there exists an integer, namely k, such that 22r plus 18s equals 2k. A non-constructive proof of existence involves showing either A, that the existence of a value of x that makes q of x true is guaranteed by an axiom or a previously proved theorem, or B, that the assumption that there is no such x leads to a contradiction. So the disadvantage of a non-constructive proof is that it may give virtually no clue about where or how x may be found. The widespread use of digital computers in recent years has led to some dissatisfaction with this aspect of non-constructive proofs, and to increased in efforts to produce constructive proofs containing directions for computer calculation of the quantity in question. Disproving universal statements by counterexample. To disprove a statement of the form for all of x in D, if P then Q, find a value of x in D for which the hypothesis P is true and the conclusion is false. Such an x is called a counterexample. Disprove the following statement by finding a counterexample. For all real numbers a and b, if a squared equals b squared, then a equals b. A squared equals b squared, but a and b do not equal. Give me a counterexample. A and B equal minus 2 and 2. Both equal, the squares both equal 4, but A and B do not equal each other. To disprove this statement, you need to find real numbers A and B such that the hypothesis A squared plus B equals B squared is true, and the conclusion A equals B is false. The fact that both positive and negative integers have positive squares helps in the search. You can flip through some possibilities in your mind. You'll likely see that minus 1 and 1 will work. You only need one such pair to give a counterexample. Statement. For all real numbers A and B, if A squared equals B squared, then A equals B is false because of the counterexample A equals 1 and B equals minus 1. So, proving universal statements. Use the method of exhaustion to prove the following statement. For all n as elements of Z integers, if n is even and n is between or equal to 4 and 26, then n can be written as the sum of two prime numbers. Well, you can go through all the combinations and write each value as a sum of two prime numbers. That would be the proof by exhaustion. You exhaust all the possibilities showing that it is true, that the statement is true. The most powerful technique for proving a universal statement is one that works regardless of the size of the domain over which the statement is quantified. It is based on a logical principle sometimes called universal generalization. A more descriptive name is generalizing from the generic particular. So generalizing from the generic particular is to show that every element of a set satisfies a certain property. Suppose X is a particular but arbitrarily chosen element of the set and show that X satisfies this property. At some time, you may need to have been shown a mathematical trick like the following. You ask a person to pick any number, add 5, multiply by 4, subtract 6, divide by 2, and subtract twice the original number. You can astound the person by announcing that their final result was 7. How does the trick work? Imagine the empty box here contains whatever number the person picked. You can show by the end of the calculations that the result would be 7. Pick a number, add 5 lines, multiply by 4, subtract 6, divide by 2, and then subtract twice the original number. So you have 7. The X in the table above is another way of representing the number the person picked. It is particular because it represents a single quantity, but is also arbitrarily chosen or generic because any number whatsoever can be put in its place. So you can generalize from the generic particular to conclude that if you follow these steps, you will always get 7, regardless of the initial value. When the method of generalizing from the generic particular is applied to a property of the form if P of X then Q of X, the result is the method of direct proof. Express the statement to be proved in the form of, for every X in D, if P of X then Q of X. Start the proof by supposing X is a particular but arbitrarily chosen element of D, for which the hypothesis P of X is true. Show that the conclusion is true by using definitions, previously established results, and the rules for logical inference. Prove that the sum of any two even integers is even. Well, let's see here. Say m and n. M equals 2r. N equals 2s. Because they're even integers. M plus n equals 2r plus 2s for some integers r and s, which equals 2 times r plus s. R plus s is an integer because addition is closed on integers. So call that equals 2t. So m and n equals 2 times some integer t. So the sum of any two even integers is even. Make sense? Kind of, sort of? Yeah. Get rid of that and we'll go to, oops. When presented with a statement to be proved, you can ask yourself whether you believe it to be true. In this case, you might imagine some pairs of even integers and mentally check that their sums are even. Since you cannot possibly choose all pairs of even numbers, you cannot show for sure that the statement is true in general by checking its truth in these particular instances. You cannot do an exhaustive proof on an infinite set. To be true in general, we'd have to show it in for it to be true in a infinite set, like even integers. To prove that the statement is true the statement in general, you need to show that no matter what even integers are given, their sum is even. But given two integers, it is possible to represent them as 2r and 2s for some integers r and s. By this distributive law, we saw the 2r plus 2s is equal to 2 times r plus s, which is even because r plus s is an integer. Thus, the statement is true in general. Suppose that the statement to be proved is much more complicated than this. What method can you use to derive a proof? You begin by expressing the statement formally. For all integers m and n, if m and n are even, then m plus n is even. Universally quantified, infinite domain. You need to to prove it in general, you need to show that no matter what two integers you might be given, if both of them are even, then their sum will also be even. Next, ask yourself, how do I start? What am I supposing? Starting point. Suppose m and n are any particular but arbitrarily chosen integers that are even. Or simply, suppose m and n are any even integers. What conclusion do I need to show in order to complete the proof? M plus n is even. Since both involve the term even integer, we must use the definition of this term, and thus you must know what it means for an integer to be even. It follows from the definition that since m and n are even, each equals twice some integer. Some of the basic laws of logic, called existential instantiation, says, in effect, that if you know something exists, you can give it a name. However, you cannot use the same name to refer to two different things, both of which are currently under discussion. If the existence of a certain kind of object is assumed or has been deduced, then it can be given a name, as long as that name is not currently being used to refer to something else in the same discussion. So, theorem 1-1. The sum of any two even integers is even. You can use that in proofs now. Getting proofs started. Believe it or not, once you understand the idea of generalizing from the generic particular and the method of direct proof, you can write the beginnings of proofs even for theorems you do not understand. The reason is that the starting point and what is to be shown in a proof depend only on the linguistic form of the statement to be proved, not the content of the statement. When the first sentence of a proof, the starting point, and the last sentence of a proof, conclusion, write the first, okay. Every complete bipartite graph is connected. So, rewrite the statement formally using a quantifier and a variable. First sentence or starting point of a proof supposes the existence of an object. In this case, G, in the domain, in the set of all graphs, that satisfies the hypothesis of the if-then part of the statement. In this case, G is a complete bipartite graph. The conclusion to be shown is just the conclusion of the if-then part of the statement. In this case, G is connected. So, starting point. Suppose G is a graph such that G is a complete bipartite. Conclusion to be shown: G is connected. Thus, the proof has the following shape. Like here, suppose G is a graph such that G is complete bipartite, yada yada yada, therefore G is connected. Fill in the blanks in the proof of the following theorem. For all integers r and s, if r is even and s is odd, then 3r plus 2s is even. Suppose r and s are any particular integers that r is even and s is odd. By theorem, was it 411? By the definition of even, r equals 2m and s equals 2n plus 1 for some integers m and n. Then 3r plus 2s equals 3 times 2m plus 2 times 2n plus 1 by substitution, which equals 6m plus 4n plus 2, which equals 2 times 3m plus 2n plus 1. Let t equal 3m plus 2n plus 1. Then t is an integer because m, n, 3, 2, and 1 are integers, and because addition and multiplication are closed on integers. Hence, 3r plus 2s equals 2t, where t is an integer. And so by the definition of even, 3r plus 2s is even, as was to be shown. And it gives the reasons that were blank. And that is it for that. Yeah. We'll jump right into the second section. More methods of proof. Why aren't you? Oh, come on now. Why are you being like this? Alright. Direct proof and counterexample. Writing advice. Directions for writing proofs of universal statements. Over the years, the following rules of style have become fairly standard for writing the final versions of proofs. Number 1, copy the statement of the theorem to be proved on your paper. Clearly mark the beginning of your proof with the word proof, just so you make it clear. Make your proof self-contained. This means that you should explain the meaning of each variable used in your proof in the body of the proof. Begin proofs by introducing initial variables and stating what kind of objects they are. Let's see here. This is similar to declaring variables and their data types at the beginning of a computer program before they are used. At a later point in your proof, you may introduce a new variable to represent a quantity that is known at that point to exist. So you can introduce variables later. You just need to declare what they are, what you know about them, what kind of objects they are, that sort of thing. Write your proof in complete grammatically correct sentences. This does not mean that you should avoid using symbols and shorthand abbreviations, just that you should incorporate them into sentences. So the proof 411 for theorem 411 can be written like this, and to read each text as a sentence, read the first equals signs as equals, and each subsequent equal sign as which equals. Keep your reader informed about the status of each statement in your proof. If your reader should your reader should never be in doubt about whether something in your proof has been assumed or established, or is still to be deduced. If something is assumed, say so. If it is still to be shown, say so. This is especially important if you introduce a variable in rephrasing what you need to show. Give a reason for each assertion in your proof. Each assertion in a proof should come directly from the hypothesis of the theorem, or follow from the definition of one of the terms in the theorem, or be a result obtained earlier in the proof, or be a mathematical result that has previously been established or is agreed to be assumed. Indicate the reason for each step of your proof using phrases such as by hypothesis, by definition of, by theorem, and so forth. Include the little words and phrases that make the logic of your arguments clear. Indicate how each sentence is related to the previous one. Start sentences with because or since to state the reason, and state the reason why it follows, or write then or thus or so or hence or therefore or consequently, or it follows that, and include the reason at the end of your sentence. If a sentence expresses a new thought or facts that does not follow as an immediate consequence of the previous statements, but is needed for a later part of a proof, introduce it by writing observe that, or note that, or recall that, or sometimes in a proof it is desirable to define a new variable in terms of previous variables. In such a case, introduce the new variable with the word let. Display equations and inequalities. Convention is to display equations and inequalities on separate lines to increase readability, both for others and ourselves, so that we can more easily check our work for accuracy. Variations among proofs. It is rare that two proofs of a given statement written by two different people are identical. Even when the basic mathematical steps are the same, the two people may use different notation or may give differing amounts of explanation for their steps, or may choose different words to link the steps together, etc. It's kind of like writing a program. A program of any length written by two different people, no matter how close they are or how much they know each other, they're going to be different. Each person has their own programming style. Proofs are the same way. Your style is going to be different from everybody else, and is unique as a fingerprint. Yeah, it's, copying quoting is, easy to track down in programming and writing of proofs, because, like I said, everybody is different. Common mistakes. Following are some of the most common mistakes people make when writing mathematical proofs. Arguing from examples. Looking at examples is one of the most helpful practices that problem solvers can engage in, and is encouraged by all good mathematics teachers. However, it is a mistake to think that a general statement can be proved by showing it to be true for some individual cases. Yeah, that's anecdotal evidence, which is not evidence, not considered valid. Like the proof that the sum of any two even integers is even It's true because if m equals 14 and n equals 6, which are both even, then m plus n equals 20, which is also even. Nah, anecdotally it's true, but you can't show it to be true across a infinite set by using examples. Can't do exhaustive proofs that way. In the same way, an argument from examples may be mistakenly used to prove a true statement. In the previous example, it was not sufficient to show that the conclusion is true for those. You must give an argument to show that the conclusion is true for any arbitrarily chosen even integers m and n. Use the same letter to mean two different things. It's like a variable in a program. You can't use it for two different things in the same program. You have a scope and it's for a variable, and you must keep track of your variables and what they mean throughout the proof. Keep it consistent. Jumping to a conclusion. To jump to a conclusion means to allege the truth of something without giving an adequate reason. Let's see here. Suppose m and n are even integers. By definition of even, m equals 2r and n equals 2s for some integers r and s. Then m plus n equals 2r plus 2s, so m plus n is even. There's some missing steps there. You're jumping to a conclusion. Assuming what is to be proved. To assume what is to be proved is a variation of jumping to a conclusion. As an example, considering the following proof, that the product of any two odd integers is odd. Suppose m and n are any odd integers. When any odd integers are multiplied, their product is odd. Hence, m plus n is odd, or m times n is odd. That's like circular reasoning. There's not, there's no proof there. There's just restating the conclusion. Confusion between what is known and what is still to be shown. A more subtle way to jump to a conclusion occurs when the conclusion is restated using a variable. Example with any two integers, the product of any two integers is odd. Suppose m and n are any odd integers. We must show that m and n is odd. Mn is odd. This means that there exists an integer s such that mn equals 2s plus 1. Also, by definition of odd, there exists an integer a and b such that m equals 2a plus 1 and n equals 2b plus 1. Then m times n equals this quantity, which equals 2s plus 1. So since s is an integer and m and n is odd by definition of odd. In this example, when the author restated the conclusion to be shown that mn is odd, the author wrote, there exists an integer s such that mn equals 2s plus 1. But we only know that the integer s exists if we know that m and n is odd, which is what the author is trying to show. Thus, the sentence starting with the word then, the author jumped to an unjustified conclusion. This mistake might be avoided if the author had written, this means that we must show that there exists an integer s such that mn equals 2s plus 1. Even better way to avoid this kind of error is not to introduce a variable into a proof unless it is either part of the hypothesis or deducible from it. Use of any when the correct word is some. There are a few situations in which the words any and some can be used interchangeably. In most situations, however, that the words any and some are not interchangeable. Here is the start of a proof that the square of any odd integer is odd, which uses any when the correct word is some. Suppose m is a particular but arbitrarily chosen odd integer. By definition of odd, m equals 2a plus 1 for any integer a. Yeah, doesn't work that way. It does not any integer a, but for some integer a. So there exists an integer a such that m equals 2a plus 1. Misuse of the word if. Another common error is not serious in itself, but it reflects imprecise thinking that sometimes leads to problems later in a proof. This error involves using the word if when the word because is really meant. Consider, suppose p is a prime number. If p is prime, then p cannot be written as a product of two smaller positive integers. But the use of if is kind of unnecessary or imprecise because we are assuming p is a prime number, so there is no if about p being prime. So because p is prime, p cannot be written as a product of two smaller positive integers. Prove that the difference of any odd integer and any even integer is odd. Use only the definitions of odd and even and the assumptions listed below, not any other properties of odd and even integers. These are the assumptions from the beginning of the chapter. Follow the directions given in the section for writing proofs and of universal statements. You may already have a sense that the statement to be proved is true, but to make sure your intuition is correct and to develop a careful proof, rewrite the statement. For all integers a and b, if a is odd and b is even, then a minus b is odd. So starting point of the proof would be something like, suppose a is any odd integer and b is any even integer. And the conclusion to be shown is we must show that a minus b is odd. If, in addition, you know that they use the definitions of odd and even, you will have reduced the creative part of the developing the proof to a small but crucial section in the middle. Which leads to theorem 4.2.1. The difference of any odd integer and any even integer is odd. Identifying a mistake in a proposed proof. Find the mistake in the following proof. If n is any even integer, then minus 1 to the n is equal to 1. So, by definition of even, n equals 2a. And then which equals then minus 1 to the n equals minus 1 to the 2a, which equals minus 1 to the a to the squared by law of exponents. because any non-zero real number squared is positive, you have to say it equals 1. But what is the problem? Incorrectly jumps to a conclusion in line 5. Although it is true that the square of any non-zero real number is positive, it does not follow that the square of minus 1 to the a is 1. Exercise 10 at the end of this section asks you to give the correct proof of this theorem. Showing that an existential statement is false. So, we know that the negation of an existential statement is universal. It follows that to prove an existential statement is false, you must prove a universal statement, its negation, is true. Show that the following statement is false. There is a positive integer n such that n squared plus 3n plus 2 is prime. Well, proving that the given statement is false is equivalent to proving the negation is true. The negation is for all positive integers n squared plus 3n plus 2 is not prime. Because the negation is universal is proved by generalizing from the generic particular. The statement, there is a positive integer such that n squared plus 3n plus 2 is prime, is false. Proof. Suppose that n is any particular but arbitrarily chosen positive integer. Factoring shows that n plus 1 times n plus 2. In addition, n plus 1 and n plus 2 are integers because they are sums of integers. And both n plus 1 is greater than 1 and n plus 2 is greater than 1. Because n is greater than 1, or equal to 1. Thus, n squared plus 3n plus 2 is a product of two integers, each greater than 1. So, n squared plus 3n plus 2 is not prime. And that is it for section 2. Let's see if we can squeeze in section 3. Are you going to behave? Yeah, okay. Direct proof and counterexample 3, rational numbers. Okay. A real number r is rational if and only if it can be expressed as a quotient of two integers with a non-zero denominator. A real number that is not rational is irrational. More formally, if r is a real number, then r is rational if and only if there exist integers a and b such that r equals a over b and b does not equal to 0. Is 10 over 3 a rational number? Yeah, pretty obvious. Is minus 5 over 36 or 39 a rational number? Yeah, minus 5 and 39, it's two integers. Is 0.281 a rational number? Yeah, 289 over 1,000. Two integers. Is 7 a rational number? Yes. Is 0 a rational number? Yeah. Is 2 over 0 a rational number? No, because it has the quotient or the denominator has to be non-zero. Is 2 over 0 an irrational number? No, because it's not a real number. If I'm not mistaken. 0.12121212 on into infinity is it a rational number? Yeah, I'd forget the ratio, but it is a rational number. If m and n are integers and neither m nor n is 0, then m plus n over m times n is a rational number. Is it? Yeah, they're integers, so yeah, it's a rational number. Let's see here. Yes, yes, yes. Yes, yes, no, because it's not a real number. Yeah, it's not a real number, and division by 0 is not allowed. And no, it's not an irrational number because it's not a real number. Yes, because, okay, 12 over 99, okay. Yeah. And yes, because the zero product property. If neither of two real numbers is 0, then their product is also not 0. Zero product property. More on generalizing from the generic particular. Most problems are stated in formal language, but solving them often requires translating them into more formal terms. Every integer is a rational number. Proving properties of rational numbers. Prove that the sum of any two rational numbers is rational. Yeah? Begin by mentally or explicitly writing the statement to be proved in the form of for all blank, if blank, then blank. Restatement. For all real numbers R and S. If R and S are rational, then R plus S is rational. Now ask yourself, what am I starting from? What am I supposing? Gives you a starting point. Then you ask yourself, what must I show to complete the proof? R plus S is rational. How do I get from the starting point to the conclusion? That's the body of the proof. Rational numbers are quotients of integers, so to say that R and S are rational means that R equals A over B and S equals C over D. For some integers A, B, C, and D, where B and D are not equal to 0. It follows by substitution that A over B plus C over D equals R plus S. So, adding fractions, you multiply things around and rewriting the fraction with common denominator, adding fractions with a common denominator. Is this fraction a ratio of integers? Yes, because the products and sums of integers are integers. And AD plus BC and BD are both integers. Is the denominator BD not equal 0? Yes, by the zero product property. Thus, R plus S is a rational number. Theorem 432, the sum of any two rational numbers is rational. Deriving new mathematics from old. Moving forward. Suppose you that you have already proved the following properties of even and odd integers. The sum, product, and difference of any two even integers are even. The sum and difference of any two odd integers are even. The product of any two odd integers is odd. And the product of any even integer and any odd integer is even. The sum of any odd integer and any even integer is odd. The difference of any odd integer minus any even integer is odd. The difference between any even integer minus any odd integer is odd. Use the properties listed above to prove that if A is any even integer and B is any odd integer, then A squared plus B squared plus 1 divided by 2 is an integer. Okay. All right. Suppose A is any even integer and B is any odd integer. By property 3, B squared is odd. By property 1, A squared is even. Then by property 5, A squared plus B squared is odd. And because 1 is also odd, the sum A squared plus B squared plus 1 is even by property 2. Hence, by definition of even, there exists an integer k such that A squared plus B squared plus 1 equals 2k. Dividing both sides by 2 gives A squared plus B squared plus 1 equals k, which is an integer. Thus, A squared plus B squared plus 1 all over 2 is an integer. Derive the following corollary as of theorem 432. The double of a rational number is rational. The double of a number is just its sum with itself. But since the sum of any two rational numbers is rational, the sum of a rational number with itself is rational. Hence, the double of a rational number is rational. And you can say it in this little, 3-sentence proof. And that will wrap up section 3, it looks like. So that'll be it for the day. We'll try to cover 3 more sections on Thursday, maybe 4. The midterm will be next Thursday, which is the 5th? 2, 3, yeah, 5th of next week. Thursday of next week will be midterm. And midterm grades are due on the 9th. So you can check Canvas or pause after that point to get your midterm grade. In the meantime, have a good day. See you on Thursday.